You've probably heard the line, our solar system is nothing special. With so many stars, there must be millions like it. Or the opposite. Earth is a one-grand fluke. Both sound strong, and both feel right, depending on which story you like more. But here's the problem. Almost everything those stories rely on is invisible to us right now. The way we look for planets makes some kinds of solar systems pop out of the data and almost hides others. Hot Jupiters look common because they are easy to spot. True Jupiter lying like giants, far from their stars, barely show up at all. We talk about Earthlike and Sunlike as if those words were clear, but when you push on them with real measurements, they start to fall apart. In this lecture, we're going to pull that whole picture apart and rebuild it from the ground up, using what Kepler, TESS, and especially Gaia are actually doing. If you want to follow the full story, subscribe, hit like so more people see this, and stay with me to the end, because the answer to, are we rare, is not what you think it is. Most people treat this question as simple. Either our solar system is normal or it is rare, and we just need to find enough other systems to know which. That feels obvious because you imagine the galaxy as a big bag of planetary system, and we are just pulling out more and more examples. We use words like typical, average, and Goldilocks as if those labels were clear and neutral, but they come before any real look at how we actually detect other systems. Our current planet lists are built from methods that strongly prefer some kinds of systems and almost ignore others. Big, close-in planets are easy to see. Distant Jupiter-like ones are not. Long orbits are hard to track. Short orbits are simple. So when you try to decide how rare our system is by just counting, you are comparing one fully seen system to many half-seen ones. The simple idea that more data will cleanly answer the rarity question depends on an intuition about fair sampling that does not apply here. That belief has to go first. We do not see our solar system the way the universe sees it. We see it through a brain that cares mainly about this one world where we live. So when we ask if our system is rare, we often mean, is a place like Earth rare? We focus on oceans, air, and comfort, not on orbits, masses, and star types. Different people then reach different answers because they start from different pictures. Some imagine many Earths. Others imagine almost none. The brain uses shortcuts, copying what it already knows. It quietly uses our system as the default model, then judges other systems by how close they feel to that model. If many people agree that our system is special or ordinary, that only proves we share similar shortcuts. It does not prove the galaxy matches them. Planetary systems form and evolve according to gravity and gas, not according to our stories. Reality does not check with our sense of normal before arranging its planets. To ask if our solar system is rare, we first need to say, in clear terms, what like ours means. Physics does not care about words like homie or Goldilocks. It cares about what we can measure. For other systems, we measure how their stars move, how their light dips when a planet passes in front, and how their positions shift on the sky. From those signals, we estimate planet sizes, masses, and distances from the stars. So a solar system analog might mean a sun-like star with small rocky planets in the inner region and a Jupiter-like giant farther out on wide, long orbits. This feels thin compared to our rich picture of seasons, moons, and life, but it is what our tools can see. Vague questions like, is our system special? Break apart when we must point to numbers instead of feelings. The language grows less warm, but the meaning grows clearer. Imagine you are flying over a continent at night, but you can only see city lights in certain colors. Bright, fast blinking lights show up easily. Dim, slow changing lights almost vanish. If you tried to map all cities from this view, you would think the world is filled mostly with one kind of city, simply because those are the ones your eyes pick out. This is close to how we study other planetary systems. The transit and Doppler methods easily find big planets close to their stars, like bright, nearby cities. Wide, cool giants like Jupiter are more like faint suburbs, hard to notice. The new astrometry method used by Gaia is like adding a different sensor that can finally see those far suburbs. The city picture is not perfect because planets interact and move in ways cities do not. But this structure-based analogy replaces the old, wrong idea that our catalog is a clear, neutral snapshot. It shows that what we call common mostly reflects how we look. When we look at real data, most known planetary systems do not look like ours. Many have giant planets skimming very close to their stars, hot Jupiters we would never expect from our own example. Others, like the TRAPPIST-1 system, have a tight chain of planets, all about the same size, packed close in like beads. Gaia has already found super-Jupiters orbiting very small stars, a mix once thought almost impossible. These results feel strange only because we trained our intuition on one system. The same rules of gravity, gas disks, and migration can make many shapes, depending on small changes in starting conditions. Nothing is broken when systems end up crowded, empty, or lopsided compared to ours. We simply did not see those patterns before. Our minds keep trying to treat our system as the template, but under extreme cases, the universe shows that there is no single real layout, only many outcomes from the same physics. It is easy to tell a story where systems start wild and then slowly settle into something calm and balanced like ours. That feels like progress, as if nature were aiming toward our layout. But the physics does not say that. Planetary systems form from spinning gas and dust disks. Small changes in the disk or in the timing of planet growth can send giant planets inward, fling smaller ones out, or leave chains of similar worlds. Many different end states are possible. The equations that describe these motions do not choose a preferred direction. They allow many paths forward and backward in time. We only remember one history, the path our system took, so we mistake it for a natural goal. When we study thousands of systems at once, that feeling of a one-way trend fades. We see a spread of outcomes instead of a ladder of improvement. An equilibrium here is just a stable mix of architectures, not a march towards something like home. It feels like we live at the right moment to answer the question, is our solar system rare? We look at today's exoplanet catalog and treat it as a clean picture of what exists now. But what we see depends on when and how we look. Kepler stared at one patch of sky for a few years and mostly found close-in planets that transit. Doppler surveys watched bright nearby stars and picked up many hot and warm giants. Gaia, over a decade, measures tiny shifts in star positions and is just starting to reveal distant Jupiter-like planets. Each method slices reality in a different way, with its own blind spots and strengths. There is no single master list that shows every system type fairly. What stays fixed underneath are the physical rules and broad trends, not our partial snapshots. Our sense that we can just read off the galaxy's true pattern right now is another intuition that breaks once we see how time and tools shape the view. By now, simple ideas have fallen away. The thought that we could just count solar systems like ours and quickly learn how rare we are no longer works. Instead, we are left with stricter ideas. We must say which star type, which planet masses and orbits, and which detection limits we mean. That is less cozy than words like special or average, but it is more honest. It also feels uncomfortable because it shows how much we do not yet know. Our language keeps trying to jump ahead, to label us as either common or unique, but the data and methods refuse that clean answer. As new missions like Gaia and TESS add more biased slices of reality, they do not give a final verdict. They force us to upgrade our question and drop old shortcuts. That can feel like going backward. In fact, it is a sign that the earlier, neat story about our place in the galaxy was too simple to survive contact with the real universe.